Good morning everyone. So, we were discussing about the transient heat conduction problems. In fact, we are discussing about the transient transport processes, and the first example we have taken as the transient heat conduction problem. Now, in a general problem, general heat transfer problem, it will be either a homogeneous boundary condition problem or a non-homogeneous boundary condition problem. And if and we have discussed in the last class, if your governing equation is linear partial differential equation, then you can go ahead with the separation of variable type of solution. And we have discussed some of the limitations of separation of variable. The number one is you must be having a non-zero initial condition and homogeneous boundary condition. Your problem may not be well defined from the very beginning such that it will be having a non-zero initial condition and homogeneous boundary condition. For a general problem, you might be having non-homogeneous boundary conditions as well as non-homogeneous initial condition. So, for that what we have decided, we will be dividing the split up the problem into sub problems, considering only one non-homogeneity at a time. Okay. Now, and then adding up all the solution, that is called principle of linear superposition. Now, I will give an example of principle of linear superposition considering an ODE first. Just consider an ordinary differential equation of order 2, let us say d square y dx square is equal to x, some arbitrary equation, okay, and subject to two boundary condition. At x equal to 0, your y is equal to, let us say 1, at x equal to 1, let us say y is equal to 2. Okay. Now, in this equation system, that means governing equation as well as the boundary condition, there are three sources of non-homogeneity. One is this, another one is this, another one is this. Okay. So, you divide, it can be, first of all, for this particular problem, solution is not very difficult, solution is straightforward, right. What will be the solution? The solution will be dy dx will be nothing but x square by 2 plus c1, y is equal to x cube by 6 plus c1x plus c2. We can put these boundary conditions and evaluate c1 and c2. Okay, that I am not doing it. Now, in order to demonstrate the principle of linear superposition, what we will be doing, since there are three sources of non-homogeneity in your equation system, we will be dividing this problem into three sub problems, taking care of one non-homogeneity at a time. Okay. The y will be basically constructed by y1 plus y2 plus y3. Okay, and you can define y1 as d square y1 dx square is equal to x, keeping this non-homogeneity and forcing the other non-homogeneities to vanish, subject to at x equal to 0, y1 equal to 0, at x equal to 1, y1 equal to 0. These equations can be constructed if you substitute this in your governing equation and take the comparable terms, collect the terms. Okay, that will be problem number 1 for y1. y2 will be what? y2 will be d square y2 dx square is equal to 0. We will be forcing this non-homogeneity to go off, keeping one non-homogeneous boundary condition intact. Like let us say x equal to 0, y2 is equal to 1, and at x equal to 1, y2 equal to 0. Okay. You can construct y3 as d square y3 dx square is equal to 0, subject to at x equal to 0, you force this boundary condition to go off, and then at x equal to 1, you keep the non-homogeneous boundary condition at y3 equal to 2. Okay. Then individually you can solve the problems and can check that solution will be same as the previous solution. Okay. Let us go in detail a little bit. D square y1 dx square equal to x, the first one, it is basically dy dx is equal to x square by 2 plus c1 y1 is basically x cube by 6 plus c1x plus c2. Okay. Put these two boundary conditions. The first condition you put means c2 is equal to 0. Okay. At x equal to 0, y1 equal to 0, this will lead you c2 equal to 0. At x equal to 1, y1 equal to 0, that will give you 0 is equal to 1 by 6 plus c1. So, c1 will be minus 1 by 6, right. So, the solution is x cube by 6 minus x by 6. Okay. Now, solve for y2, the d square y2 dx square is equal to 0, the solution is nothing but c1x plus c2. Okay. At x equal to 0, y2 is equal to 1, that means 1 is c2. Okay. So, y2 is nothing but c1x plus 1. At x equal to 1, y2 is equal to 0, that means this is 0, c1 plus 1, so c1 is minus 1. So, y2 is basically nothing but 1 minus x. Okay. Similarly, the part y3, again d square y3 dx square equal to 0, the solution is c1x plus c2 subject to x equal to 0, y3 equal to 0, that means c2 equal to 0. So, y3 is basically linear with x, and at x equal to 1, y3 is equal to 2, so c1 is equal to 2. So, y3 will be equal to 2x. Now, the actual solution will be a linear superposition of all these three individual solutions. Summation of yi, I will be number of equations you are having in your system. So, y1 plus y2 plus y3. y1 is x cube by 6 minus x by 6 plus 1 minus x plus 2x. Okay. X cube by 6 minus this 7 by 6, right, 7 by 6 plus 12, it will be plus 5 by 6 x plus 1. Okay. This will be actual solution, and the first straightforward solution that you have already got, you just check that this will be identical with the other one, the first one. Okay. So, this gives you a demonstration of how to use the principle of linear superposition. So, basically depending of number of homogeneities or sources of non-homogeneities that you are having in your system, you break down the problem into those number of equations taking care of one non-homogeneity at a time. Now, let us extend this analysis for a partial differential equation. Just consider a partial differential equation of this form: del u del t is equal to del square u del x square. Okay. That will be general heat conduction problem, unless and until there will be some additional term here, some algebraic term will be here, if there will be a source or sink term present in your system. Okay. In generally, the source and sink term will come if you do an energy balance for a reactive system. If it is exothermic reaction, there will be source of energy that will be coming out. Okay. So, general heat conduction problem will be in this form, transient heat conduction in one dimensional. If you have two dimensional heat conduction problem, then it will be del u del t is equal to del square u del x square plus del square u del y square. Okay. The boundary, the initial condition will be at t equal to 0, let us say a general one, u is equal to u0, okay, for any x. At x equal to 0, u is equal to, let us say u01, and at x equal to 1, u is equal to u02 for any time t. Okay. Now, we would like to solve this is a linear partial differential equation, a parabolic one, and non-homogeneous initial and boundary conditions. So, there are three sources of non-homogeneity in this equation. One is in the initial condition, another is in the boundary condition, and third one is also on the boundary. So, this problem will be divided into three sub problems considering one non-homogeneity at a time and forcing the other non-homogeneities to vanish. U is equal to U1 plus U2 plus U3. Okay. You substitute here this equation into the governing equation and collect the similar terms. So, the governing equation of U1 you will be getting as del U1 del T and del square U1 del x square. Okay. Now, the initial condition, let us say we keep this non-homogeneity intact and force the other two non-homogeneities to go off. X equal to 1, your U1 is equal to 0. Now, this is a linear partial differential equation, non-zero initial condition and homogeneous boundary condition. So, your separation of variable can be used as it is in this particular problem. Use separation of variable. Okay. Now, the other two parts are very interesting. Let us construct the solution for U2. Del U2 del T is equal to del square U2 del x square, subject to at t equal to 0, your U2 equal to 0, force the U2 to go off. At x equal to 0, you keep that non-homogeneity U is equal to U01 and force the other non-homogeneity to go off. At x equal to 1, U2 is equal to 0. Okay. Now, you are having a 0 initial condition, you are having a non-homogeneous boundary condition. So, you cannot use separation of variable, you cannot apply separation of variable in this system. Okay. For that, for applying separation of variable, what you have to do? You have to again divide this problem into two sub problems. One will be a function of x only, that will be the steady state solution. Another will be function of x and t both. Okay. That means, I will be dividing this problem U2 into two sub problems. One will be the steady state solution, that will be independent of time. U2s, that will be function of x only, and U2t, that will be time varying part, that will be function of x and t both. Okay. Now, we would like to have the governing equation and boundary condition for these two parts. For that, what you have to do? You substitute U2 into your governing equation and collect the terms. Del U2 del T will be nothing but del U2t del T, because it will be function of x only. U2s is a function of x only. Okay. And on the right hand side, you will be having d square U2x dx square plus del square U2t del x square. That means, if you substitute this equation in your governing equation, what you will be getting? You will be getting del U2t del T is equal to nothing but d square U2s, it will be a sole function of x dx square plus del square U2t del x square. Now, we collect the terms. Governing equation for U2s will be d square U2s dx square is equal to 0, and for U2t it will be del U2t del T is equal to del square U2t del x square. Okay. Now, we will be getting the boundary condition and initial condition of these two systems. Now, let us concentrate on U2s, the steady state part. The governing equation is d square U2s dx square is equal to 0. Your original problem was at x equal to 0, U2 is equal to U01. U2 is equal to U01. That was your original problem for the part U2, for the second problem. And U2 we are dividing into U2s plus U2t. So, it will be U2s plus U2t is equal to U01. Now, here lies the trick. You collect the terms and let the non-homogeneous part of your boundary condition to go away with U2s. Okay. Select non-homogeneous part with the steady state solution U2s. That means, U2s is equal to U01 at x equal to 0, and of course, if that is the case, then U2t will be equal to 0, right. U2t will be equal to 0. At x equal to 1, your U2 is equal to 0. And what is U2? U2 is nothing but U2s plus U2t is equal to 0. That means, each of them will be 0 at the boundary x equal to 1. That is pretty straightforward. At x equal to 1, U2s is equal to 0 and U2t is equal to 0. Okay. So, is that all right? Should I repeat it? Okay. The formulation of this is not a problem, I think, right? Okay. Now, let us fix the boundary condition and initial condition. At x equal to 0, U2 in the original problem U2 was equal to U01. What is U2? U2 is nothing but U2s plus U2t. And we apply a trick here, a mathematical treatment, that is, we allow the non-homogeneous part to go along with U2s, the steady state solution. That means, U2s will be equal to U01 at x equal to 0. That means, at x equal to 0, U2t equal to 0. So, we get the boundary condition of U2s at x equal to 0, we get the boundary condition of U2t at x equal to 0, fine. And in the original problem, my U2 was equal to 0 at x equal to 1. Right. What is U2? U2 is nothing but U2s plus U2t. So, each of them will have to be 0 at x equal to 1. In this process, what you are getting two boundary conditions of U2s, you are getting two boundary conditions of U2t. Note that these two boundary conditions of U2t are homogeneous now. Now, let us clearly write down the U2s is equal to 0 at x equal to 0, U2s is equal to U01, at x equal to 1, U2s is equal to 0. Okay. Now, what is the solution? U2s is equal to C1x plus C2, at x equal to 0, U2s is equal to U01, that means C2 equal to U01. If we apply the first boundary condition, you will be getting C2 is equal to U01. That means U2s is equal to U01 plus C1x. At x equal to 1, U2s is equal to 0. That means this is 0, U01 plus C1. That means C1 is nothing but minus U01. Okay. So, what is the solution? The steady state solution is U01 into 1 minus x. Okay. That is the steady state solution. Okay. Now, let us go back and get down the next part, the U2t. This is del U2t, del t is equal to del square U2t del x square. At x equal to 0, we have already found out U2t is equal to 0. At x equal to 1, U2t is equal to 0. That you have already found out, right? Now, let us find out the initial condition. What was the initial condition? At t equal to 0, your u2 was is equal to 0, right? And what is u2? u2 is nothing but u2s, which is a function of x plus u2t is equal to 0. That means u2t is nothing but minus u2s, which is a function of x. Okay. So, your u2t is equal to minus u01 into 1 minus x at time t is equal to 0. Now, see, in this part, this has become a non-zero initial condition and homogeneous boundary condition. Okay. So, you can apply separation of variable as it is now. Now, you can apply a separation of variable solution. And your u2 will be constructed as a solution of u2s plus u2t. We will be looking into separation of variable solution later on. Okay. So, your u2 will be nothing but u2s plus u2t. This is a function of x only, this is a function of x and t both. Now, let us look into the third problem, u3. What is u3? u3 was del u3 del t is equal to del square u3 del x square at t equal to 0. Your u3 was equal to 0, at x equal to 0, u3 was 0, at x equal to 1, u3 was u30 or what is that? u02 probably, whatever it is, fine. Now, again, since you are having a 0 initial condition and a one non-homogeneous boundary condition, you again divide this problem into two sub-problems. Okay. u3, one will be time independent, that will be a steady state solution, another will be the time dependent as well as space dependent. u3 will be u3s, which is a function of x only, and u3t, which will be function of x and t both. Okay. Substitute this here, and like the previous one, you get the governing equation of u3s. u3s will be nothing but d square u3s dx square is equal to 0, and u3t will be nothing but del u3t del t is equal to del square u3t del x square. Okay. Now, what is left is to find out the boundary conditions, two boundary conditions for this problem, one initial condition and two boundary condition for this problem. Now, let us find that at x, it is exactly like the u2, the case of u2. Okay. In this case, you allow the non-homogeneous boundary condition to go away, to go along with u3s. That will force the boundary condition of u3t to be homogeneous at this boundary x equal to 1, and on the other boundary it is already 0. Let us say at x equal to 0, your u3 was equal to 0. What is u3? u3 is nothing but u3s plus u3t. That means each of them will be equal to 0 at x equal to 0. At x equal to 1, your u3 was u02. u3 is it consists of u3s plus u3t is equal to u02. Now, you allow this non-homogeneous boundary condition value to go along with u3s. u3s is u02 and u3t is equal to 0. That will force the boundary conditions of time varying part to be 0, and the initial condition. So, basically these two will be constituting the boundary condition for u3s at x equal to 0 and at x equal to 1. Okay, that is straightforward. I am not doing that again. For u3t, this will be the boundary condition at x equal to 0. This will be the boundary condition at x equal to 1. They are homogeneous. Now, what is left is the initial condition of u3t. At t is equal to 0, your u3 was equal to 0, So, u3t will be nothing but minus u3s, which will be sole function of x. You will be having the steady state solution first. That steady state solution will become the initial condition of the transient problem. Okay. So, u3t is now a standard problem with a non-zero initial condition and homogeneous boundary condition, and can be solved using separation of variable. Okay. Now, your overall solution will be constructed by addition of all these solutions by using principle of linear superposition. Okay.
Could you suggest a book where this discussion?
No, here. No. Now, the point is, I have talked about this, discussed this problem, because these will be the general problem appearing in any heat conduction problem or any systems where you will be having non-zero initial and the non-homogeneous initial and the boundary conditions. Your problem may not be well posed all the time that you will be getting homogeneous boundary condition. Okay. It is not that for this particular problem you are having two variables. Suppose you are having a steady state problem, but two dimensional steady state problem. In that case, suppose you are having an equation something like this: del u3 del x is equal to del square u3 del y square. In that case, let us say at t equal to 0, your u3 is equal to 0, at x equal to 0, your u3 is equal to 0, at x equal to 1, your u3 is equal to, let us say, u02. This is a different problem. Suppose this is a two-dimensional steady state problem. This is not a heat conduction problem. Whatever I am discussing, there is a general issue altogether. Suppose it is not a heat conduction problem. Okay, it is a steady state two-dimensional problem. Steady state means time independent. There is no time variable here. Sorry, these are x yes, these are x equal to 0, these are y equal to 0, and these are y equal to 1. In that case, again this problem will be divided into two subparts. One will be a function of y alone, and another will be function of x and y both. Look into the similarity. This problem will be divided into two problems. u3 whatever u3s you can say as a function of y only, and u3 prime, which is a function of x and y both, and you can proceed the similar way. The procedure remains the same. Now, let us look into a typical heat conduction problem. Now, if you do the energy balance and one dimensional transient, okay, the governing equation of the energy equation it becomes del T rho Cp del T is equal to K del square T del x square, right. So, this becomes del T is equal to alpha del square T del x square. This is alpha is known as the thermal diffusivity, K by rho Cp. Now, at t equal to 0, let us say t is equal to T naught, at x equal to 0, t is equal to T10, at x equal to 1, t is equal to, let us say, T20. Now, there are again three sources of non-homogeneity. What you can do, you can reduce the load of computation by defining a variable theta as t minus T10 or T20, does not matter. If you do that, if you define it like this, then your governing equation becomes del theta del T is equal to alpha del square theta del x square. At t is equal to 0, your t was equal to T naught, so your theta becomes, let us say, theta naught, that is nothing but T0 minus T10. At x equal to 0, theta is equal to 0, at x equal to 1, theta is equal to, let us say, theta 20, that is T20 minus T10. Okay. So, in this case what you have done, you have done basically you have shifted the temperature scale and define a new variable theta is T minus T10. What is the advantage of it? You forced one of the boundary condition to be homogeneous. So, now there are only two sources of non-homogeneities in this problem, right. Okay. So, what we are going to do, we are not dividing this problem into 3 subparts, we are going to split down this problem into 2 parts. Let us say theta is equal to theta 1 plus theta 2, del theta 1 del t is, let us say, write down for the theta 1, del theta 1 del t is equal to alpha del square theta 1 del x square at t is equal to 0. Your theta 1 is equal to, let us say we keep this non-homogeneity and force the boundary conditions to be homogeneous. At x equal to 0, your theta 1 is equal to 0, at x equal to 1, your theta 1 is equal to 0. Okay. Now, again this is having a non-zero initial condition and homogeneous boundary conditions. So, you can apply separation of variable straight away. Okay. For the other part theta 2, it will be del theta 2 del t is equal to del square theta 2 del x square. We force the initial condition to go off this time at t equal to 0, your theta 2 is equal to 0 at, okay, alpha will be there, fine. Alpha is constant, means since it is a linear problem, rho, CPK, all these physical and thermophysical properties are independent of temperature, that is assumed. At x equal to 0, your theta 2 was equal to 0, and at x equal to 1, we keep the non-homogeneity this time in this problem. Since it is having a 0 initial condition and non-homogeneous set of boundary conditions, this problem again will be divided into 2 subparts. One will be the steady state part, that will be time independent part, another will be time dependent part. So, theta 2 will be basically theta 2 s, which will be function of x only, and theta 2 t, which will be function of x and t both. Okay. So, the governing equation of theta 2 s will be d square theta 2 s dx square is equal to 0. The boundary condition can be derived exactly similar way as previously. At x equal to 0, your theta 2 s is equal to 0, at x equal to 1, your theta 2 s is equal to theta 2 0. You allow the non-homogeneous boundary condition to go along with the theta 2 s, that will force the boundary condition of theta 2 t to be 0. So, this will be set of equation for theta 2 s, and for theta 2 t the governing equation becomes del theta 2 t del t is equal to alpha del square theta 2 t del x square, and the initial condition that can be derived as previously, theta 2 t will be is equal to minus theta 2 s, which will be function of x only at time t is equal to 0, and for any time t at x equal to 0, your theta 2 t is equal to 0, for x equal to 1, your theta 2 t is equal to 0. Now, you are having a non-zero initial condition and set of 0 boundary conditions. Again, this problem can be solved using separation of variable. So, overall solution of theta 2 can be constructed as theta 2 s, which will be function of x, plus theta 2 t, which will be function of x and t both. Okay. And the final solution theta will be t minus t 0 1, theta 1 plus theta 2 plus, that is it, theta 1 plus theta 2, and theta 2 will be theta 2s plus theta 2t. Okay. Now, we will be showing some of the actual problems in the transient heat conduction now using separation of variable. Now, we will be taking off all possible boundary conditions, means Differential boundary condition, that means constant temperature condition. One of the boundary is, let us say, a constant heat flux is coming in, or it is insulated, that means derivative of temperature is off at that boundary, and it is open to atmosphere, that is a mixed boundary condition, conduction plus convection. Let us take the first one, del T is equal to alpha del square T del x square. At T is equal to 0, or capital T is equal to T0, at x equal to 0 and at x equal to 1, let us say you are maintaining same temperature, T is equal to T1 in both the cases. Okay. So, these are basically the Differential boundary condition that we have discussed previously. Now, we define a variable theta as T minus T1. So, this becomes a very well posed problem. Del theta del T is alpha del square theta del x square. At T is equal to 0, theta becomes, let us say, theta 0, that is nothing but T0 minus T1 for any T. At x equal to 0, your theta is equal to 0, and at x equal to 1, your theta equal to 0. Okay. So, this is basically a standard separation of variable problem solution. Okay. Now, in separation of variable, you assume that solution is constituted by two parts, product of two parts, one is time varying only, another is space varying only. Let us say theta is a function of some function of tau of t only, let us say capital X, which is a function of x only. Now, you substitute this in your governing equation, del theta del t is equal to alpha del square theta del x square. If you do that, this becomes x d tau dt is equal to alpha tau d square x dx square, right. Correct the terms, 1 by alpha is constant, alpha tau d tau dt is equal to 1 by x d square x dx square. Okay. Now, this is a function of time alone, this is a function of space alone, they are equal, that means they have to be equal to some constant. Now, this constant can be 0, can be positive, can be negative. We have already seen in the last class, if this constant becomes 0, then this problem becomes a trivial problem, the solution becomes a trivial solution, and we are not looking for that. If this constant is positive, it is on the other side now. If it is a positive, then again you will be landing up with a trivial solution. So, this constant has to be a negative one. So, let us say this constant is minus lambda square. Okay. So, let us solve the time varying part, alpha tau d tau dt is equal to minus lambda square. So, the solution of this is nothing but time varying part is some constant, let us say Ct exponential minus lambda square alpha t. Okay. That is the solution of the time varying part. Okay. Now, let us look into the solution of the once you get the time varying part, let us look into the solution of the space varying part, that is d square x dx square plus lambda square x is equal to 0. x square plus lambda square x is equal to 0 subject to two boundary conditions of the original problem have to be satisfied by the boundary condition of the spatial variation, because boundary conditions are in the spatial direction, in the x direction only in the original problem. Okay. In the original problem, your boundary conditions at x equal to 0 and x equal to 1 are specified. Those boundary conditions must be satisfied by the spatial variation part. Okay. That means at x equal to 0, your capital X was equal to 0, and at x equal to 1, the same boundary condition prevails. Now, you see, this becomes an ODE of this form with the homogeneous boundary condition. What this problem is called, that we have discussed in the last class. This is called a standard eigenvalue problem. This is in the same form as a standard eigenvalue problem. Or the Sturm-Liouville problem. Okay. The solution of x is nothing but C1 sin lambda x plus cosine lambda x. Okay. Now, if you put the first boundary condition x equal to 0 plus C2. Okay. If you put the first boundary condition at x equal to 0, your capital X equal to 0, that will force C2 to go off from boundary condition at x equal to 0. Okay. That means x is equal to C1 sin lambda x. Now, if you put the other boundary condition at x equal to 0, x equal to 1, your capital X is equal to 0, C1 sin lambda. To get a non-trivial solution, C1 must be equal to, must be non-zero. Okay. That means sin lambda equal to 0. So, n number of solutions exist, right? Sine curves will cut the x axis at infinite number of times. So, root of these equations are tending to infinity. So, lambda is equal to n pi, and corresponding solution is denoted by putting a subscript as lambda n. The index n runs from 1 to infinity. So, these are called the eigenvalues of the system, and the corresponding solution is the eigenfunction. X n is, let us say, C1 sin lambda n x, that means n pi x. These are the eigenfunctions. What is tau? If you remember, tau was some constant, the time varying part, exponential minus lambda square alpha t. Okay. Now, for n number of lambda, there will be having n number of tau. So, we described for the corresponding nth solution as tau n, let us say Ct exponential minus lambda n square, that is n square pi square in this case, alpha t. So, what is the overall solution? It is the product of time varying part and space varying part. Theta was theta n, the nth solution was corresponding to nth eigenvalue x n tau n. Okay. So, this is a constant, this is a constant, the product of the two will be a new constant. Let us say Cn exponential minus n square pi square alpha t sin n pi x. Okay. That is the nth solution, that means the solution corresponding to nth eigenvalue. Now, the actual solution will be constructed by linear superposition of all these solutions.
So, it is always positive.
N.
Yes, it is always positive, it can be negative.
N is running from 1, 2, 3 up to infinity, ever positive. There is a solution of sin lambda is equal to 0. Which one? N will be from 1, 2, 3. N is a positive integer. That is a solution of sin lambda equal to 0.
So what he is saying is sin lambda equal to 0. So lambda can be minus 2 pi also.
It's depending on the notation. It's depending on notation only.
Sin of minus 2 pi is also equal to 0. So
That's fine.
so we are saying n can be also equal to minus 2. So we have written n is only positive. We are saying n can also be negative.
Fine. Okay. But that does not affect in the solution, I think. That doesn't affect in the solution. Okay, so what is the actual theta will be? Theta will be summation of all the n contributions. N is equal to 1 to infinity, and this will be Cn exponential minus n square pi square alpha t sin n pi x. Okay. Now you are leaving behind with only one constant to be evaluated, that is Cn. If you know this constant Cn, then the whole solution will be known to you. You can know this constant. What is the conditions that you have supplied with? That there are three conditions you have been supplied with. One was the condition at t equal to 0. Another was the condition for x equal to 0 and x equal to 1 at any time of t. You have used up these two conditions, but you have not used up this condition. So this constant will be evaluated from the initial condition. That means at t equal to 0, your theta was equal to theta 0. Okay, that is t1 minus t0 whatever. So it becomes theta 0 Cn sin n pi x. Okay. And now this constant can be evaluated by a property which is known as the orthogonal property of the sine and cosine functions. Okay. What is the orthogonal property? That integration sin n pi x sin m pi x dx is equal to 0 for m not equal to n. 0 to 1 cosine n pi x cosine m pi x dx is equal to 0 for m not equal to n. Okay. You can prove these relations. Now, the sine functions and cosine functions will follow the orthogonal property. By using this property, you can evaluate this constant Cn. That means you multiply both sides by sin m pi x dx and integrate out between the domain 0 to 1. Okay. 0 to 1 theta 0 sin m pi x dx is equal to Cn sin n pi x sin m pi x dx is equal to 1 to infinity. Okay. So this will be 0 to 1 sin m pi x dx. Now, if you open up this summation series, all the term will vanish because of the orthogonal property, apart from one term, that is m equal to n. So this whole summation will be converted into one term only, that will be Cn sin square n pi x dx. What is the value of this? You multiply and divide by half, it will be 2 sin square n pi x, it will be what is that, 1 minus cosine 2 n pi x, okay, and cosine 2 integration of cosine 2 n pi x will lead to 0. So, it will be basically Cn by 2. Now, since m and n are running index, Cn will be 2 theta 0, 0 to 1 sin m pi x dx. Now, we can change m into n because they are running index basically. Cn will be 2 theta 0, 0 to 1 sin n pi x dx. Okay. So, this becomes 2 theta 0, what is this, minus cosine n pi x by n pi. Zero to 1. So, Cn will be 2 theta 0, 1 minus cosine n pi divided by n pi. Okay. Right. So, there will be negative sign that will be coming into it. Okay. So, the whole solution will be constructed now. Theta is nothing but t minus t0 is Cn exponential minus n square pi square alpha t sin n pi x 1 to infinity, and this Cn is basically t as a function of x and t, t0 plus what is Cn, that is 2 theta 0, theta 0 is t01 minus t0, right, divided by n pi. No, this will be within the summation 1 minus cosine n pi by n pi exponential of this thing as sine. Okay. Now, for any x you can get, for any x location you can get a profile of t as a function of time. Okay. For any time you can get a t as a function of x. For any x, particular x and t, you will be getting the point value of temperature at that particular location and at that particular instance. Now, if you look into this summation, now how will you compute it? That is one problem, because there are infinite number of terms in this summation series, and these terms will be pi, 2 pi, 3 pi, 4 pi, something like that. Now, if you go up with the higher order of eigenvalues, because of this term n square pi square, the pi square itself is around 10. Pi is 3.14, pi square itself is around 10. Okay. For n is equal to 1, this term itself will be around 10. For n equal to 2, this term will be exponential minus 40. For 3, it will be 90. Okay. So, as you go up with for the higher eigenvalue, this exponential minus term will be very dominant and the whole term will become very less. For the contribution of higher eigenvalues will be very less towards the solution of the problem. So, you need not to compute beyond 4 or 5 eigenvalues. You need not to compute this summation for infinite number of n's. You can go up to third or fourth eigenvalue and see the change. The incorporation of the next eigenvalue or the sixth eigenvalue will be probably reflecting in a slight change, let us say in the fourth place decimal or something like that. So, it is not required to go for higher eigenvalue calculation for evaluating this summation series. 4 or 5 terms will be good enough. Okay. Now, the whole solution will be changed if you have a separate set of boundary conditions, either a Neumann boundary condition or mixed boundary condition. We will continue this discussion in the next class. Thank you. Well, good morning everyone. We are looking into the transient transport processes and various examples of that. First category of examples of transient transport processes you have taken is transient heat conduction problem. Now, basically we are looking for the analytical solutions of transient heat conduction problem in the first case, and separation of variable is our tool to solve the problems, the transient heat conduction problem having homogeneous, non-homogeneous or mixed boundary conditions. Now, we have seen that if you have Dirichlet boundary conditions as existing in your boundary, then n pi will be the eigenvalues and sin n pi x will be the eigenfunctions for your solution. Then since you will be having infinite number of eigenvalues, you will be having correspondingly infinite number of eigenfunctions, and when you superpose all these eigenfunctions, you will be constructing the overall solution, which will be having only one constant that has to be evaluated. That constant has to be evaluated from the initial condition that is till unused in your solution scheme, and using that initial condition you will be able to find out what is that the unknown constant in terms of n. So, ultimately you will be getting a series solution. Now, the point comes, suppose you would like to compute some value of temperature or something at a particular location and at a particular time, then how many terms of your series solution you will be taking? It will be turning out that if you take at least first 4 or 5 terms, that will be good enough, because you will be having two parts, one is time dependent and another will be time independent part. In the time dependent part, it will be exponential minus n square pi square value itself is around 10. So, as you go up in higher eigenvalues, it will be e to the power minus 40 times something, minus 60 times something. So, that contribution will be very small. So, overall contribution of higher eigenvalues will be very small towards your solution. So, if you take first 4 or 5 eigenvalues, that will be good enough for your computation. So, you need not to evaluate all the terms in your very high number of eigenvalues in your summation series. Now, if you have Dirichlet boundary conditions, like if your boundary conditions are like at x equal to 0, let us say theta is equal to 0, at x equal to 1, theta equal to 0, you will be getting n pi as the eigenvalues and sin n pi x as the eigenfunctions. Now, we will be considering some more general cases, where these eigenvalues and eigenfunctions will be changed. For example, if you have a Neumann boundary condition, that means a derivative boundary condition existing at x equal to 0, that means at x equal to 0, let us say minus k del theta del x is equal to 0. This